The ratio test with endpoints, part 1. In earlier videos, we looked at the ratio test, how to use it. We found a radius and interval of convergence, but we never tested the endpoints. In this video, we will do the same thing as we did in the previous videos, but we will also test endpoints. So let's remind ourselves what the ratio test is. Consider a series, and then we take the ratio of a sub n plus 1 over a sub n and see what happens as n goes to infinity. So recall that we are trying to mimic a geometric series. At least way out in infinity where things matter. So if this ratio is less than 1, we know that the series converges. In fact, it converges absolutely because we're doing the absolute value. If this ratio is greater than 1, then the series diverges. What's different than the geometric series is when the ratio test equals 1. In this case, we don't know what happens, and we have to use a different test. So really, most of the other tests we learned in between ratio test without endpoints and now ratio test with endpoints, those are tests that we can use just to see if our series converges at the endpoints of our interval. Let's take a look at one example here. Consider a function f of x which equals the sum of -1 to the n times x minus 5 to the n all over n plus 1 times 2 to the n. We want to find the radius and interval of convergence and say, what does the interval of convergence really mean? So I'm going to preface this last question right now. We'll get back to it. But you need to think of f of x as a closed form function. I don't necessarily know what it is, but in other examples, it might have been sine of x, cosine of x, whatever. And then the series is the polynomial, which we hope converges to, that is, exactly equals f, our closed form function, on some interval. Let's go back to the first part. Let's find the radius and interval of convergence. Both of these terms, radius and interval of convergence, are huge clues that we want to do the ratio test. So let's do the limit as n goes to infinity. Of our nth plus 1 term, I will leave off the -1 to the n because of the absolute values. So x minus 5 to the n plus 1 over n plus 2 times 2 to the n plus 1 divided by the nth term, but we will flip and multiply instead. So n plus 1 times 2 to the n over x minus 5 to the n. And we will simplify it. I already know that there will be no n's left over, so I don't need to write the limit anymore. The n plus 1 over n plus 2 goes to 1. The x minus 5 terms go to x minus 5 on top, and then we have just a 2 on the bottom. This is my ratio way out at infinity, which means I can guarantee convergence if this ratio is between -1 and 1, or if x minus 5 is less than 2. So recall that 2 is our radius of convergence. And here's how we interpret this whole thing. I have a center 5. I want to find all x's that are no more than 2 away from my center of 5. So the interval of convergence is all x's between 3 and 7, guaranteed. But what happens at the endpoints? That is, when x equals 3 or x equals 7, the ratio test fails, but this series might converge or it might diverge. How do we determine that? It's pretty straightforward. All we need to do is put these values of x, the endpoints, into our series. Now the -1 to the n becomes very important when we're plugging back into the series with our endpoints. So I'll write as -1 to the n. And then x equals 7 gives me 7 minus 5, or 2 to the n, over n plus 1 times 2 to the n. I'm leaving off the limits on my series. It's 0 to infinity. But see how I can simplify this. The 2 to the n's cancel, and we're left with -1 to the n over n plus 1. This is an alternating series. Whose positive terms decrease to 0, which means that series would converge. So x equals 7, we have convergence. How about at x equals 3? Once again, plugging in, we get -1 to the n. I still need that. And then I get 3 minus 5 to the n, which is -2 to the n, over n plus 1 times 2 to the n. We can simplify this as well. This becomes -1 to the n. And then I'll separate out the -2 to the n, which is -1 to the n times 2 to the n, over n plus 1 times 2 to the n. Two to n's cancel again. I'll simplify at least one more time. So notice I have -1 to the n plus n, or -1 to the 2n, over n plus 1. (2n) is even. -1 to an even power is always +1. So this simplifies all the way down to the sum of 1 plus n. And by either the limit comparison, the one I would choose, or the integral test, I see that this series at the endpoint x equals 3 diverges. So to finish it off, the radius of convergence is 2. The interval of convergence is 3 less than x less than or equal to 7. So once again, what does this interval of convergence mean? That means on the interval 3 less than x less than or equal to 7, my series exactly conforms to, exactly equals some closed form function.